Hi, everybody. We are moving on to our last session of the symposium, and we have 4 student presenters that are vying for the Jeff Riley Memorial Scholarship that has been generously donated and funded by Medtronic. So first up, we have Taylor Viana.
Hello, good afternoon. I wanted to thank EPIC for allowing me to have the stage to present all of this. And I also wanted to thank, before I move forward, all of the other lovely names that you see on the slide here, because this project was not a solo effort. So a special thank you to Nikki Rosano, Salia Gordon, Sarah Hussein, and our professor, Edward Delaney, without whom we would not have been able to complete this. So let's get into it, because my project is pressure drop and handheld cannula using the Quest MPS 3. So we need to start with an essential question of what is pressure drop? So pressure drop, for the sake of our project, is the difference in pressure on one side tubing versus the other. So you lose pressure as fluid moves through a tubing. And so it happens for a variety of reasons that some really smart people figured out. And so they have all these fun laws named after them. So the first one is Poiseuille's law. I rewrote the equation below so that it's a function of pressure change. But it essentially states that a change in pressure is affected by your flow, which is Q, your viscosity, which is that long N, the length of the tubing, which is L, and the radius of the tubing, which is R. So as you have higher flows, higher viscosity, higher lengths of tubing, and a smaller radius of that tubing, you're going to have more drop when you go from one end to the other. The next thing is the Venturi effect. So this essentially explains that if you have a constrainment in your tubing, you're going to lose pressure in the constrained section. So the pressure you start with is not the pressure you end up with, even when you open back up after the constrainment. And the last part is the Bernoulli equation on the bottom. And so the Bernoulli equation, while it also governs the Venturi effect, I mostly added here because it adds in height as a variable. So if you have changes in height in your tubing, that's also going to affect the amount of pressure drop you experience. So why do we care? Well, the biggest reason we care about any of this pressure drop nonsense is because we need to ensure adequate perfusion. So our pressure drops, specifically when we're talking about cardioplegia delivery, which is what my project is focused on, it's important because we need to ensure that we are adequately delivering cardioplegia to the heart. If you deliver it with a pressure that's too low, you're not going to be able to overcome the coronary vasculature resistance, and you're not going to reach all parts of it, and you can end up with ischemic damage. But if you deliver it too high, then you're going to damage the vasculature you're trying to protect. So not super ideal. So why we want to track pressure drop is so that we can enter and maintain that Goldilocks zone of pressure while we're delivering, so that we have optimized myocardial protection. However, as we did our literature review for this project, there is not a lot of research on handheld cannula and safe cardioplegia delivery pressures when going directly down the coronary arteries through your coronary ostia. So the next bit to add in here is, what is microplegia? So microplegia is Quest Medical's Pure Blood initiative. It's a whole blood cardioplegia alternative to the traditional blood-based or crystalloid cardioplegia solutions. So when we're talking about a whole blood cardioplegia, we're talking about the most viscous cardioplegia on the market. That's very important. So put that nugget in your back pocket. It comes to haunt you later. So when we are talking about whole blood cardioplegia, it's removing that crystalloid portion that provides myocardial protection in other cardioplegia samples. And so a big reason people would like to use microplegia is that by using blood as the sole buffer and delivery medium, in conjunction with using the Quest MPS 3 delivery system, perfusionists can deliver more exact quantities of cardioplegia to arrest and protect the heart, as well as avoiding the hemodilution and improving patient safety. Additionally, using microplegia can allow individuals to retain their original hospital protocols and cardioplegia preferences, because a lot of popular solutions can be made micro for their purposes. So here are the other benefits of using microplegia. So we reduce hemodilution, we enhance oxygen delivery, we maintain buffering capabilities, and we can be cost effective and flexible. So a lot of this has to do with the lack of hemodilution and subsequent myocardial edema. And so that can be best illustrated on this slide. So as you can see here, we have two slices of myocardium. One has been treated with microplegia, kindly labeled microplegia, and the other one has been treated with 4:1 blood cardioplegia, also kindly labeled 4:1. And the biggest difference in these two images is there is more white space on the 4:1 image than there is on the microplegia image. And this is the myocardial edema that we're talking about that negatively impacts contractile myocyte function. So what is extra interesting about this slide is that 4:1 blood cardioplegia, which is 4 parts blood and 1 part crystalloid, is probably the closest neighbor to microplegia that we currently have, and yet we see a noticeable amount of edema differences. So just a nugget to keep in mind. But beyond the patient, we also have hospital-wide benefits of using microplegia solutions, which can be seen here. A lot of it is faster recovery, ICU stays, and saved costs all around. So if we're trying to put in all my ramblings together in one happy little package, that would be the pressure flow graphs that we use to help guide our cannula selection choices. So as perfusionists and as clinicians, we want to make sure we're using the right equipment to get that adequate ideal flow and adequate ideal perfusion pressure to properly protect all of the organs we're trying to protect. And so the pressure flow graphs provided by manufacturers do just that for just their cannula. So from tip to tip of the cannula, they have a water perfusate and they measure the drop experienced. However, these graphs are not designed to capture the entirety of the drop that we know exists in the clinical setting, such as the difference in the height of the cardioplegia delivery system and the patient, or differences in viscosity, as we know blood is more viscous than water. So microplegia, this is the nugget I had before, is very viscous because it's composed of entirely blood. So it's least likely to emulate these findings. And that led us to our clinical question of, if we're going to use the Quest MPS 3, what effect does delivery rate and height have on the pressure drop in these different handheld cannulas? Knowing that there are major differences in the perfusate, we had to come up with something that was like blood. So for many reasons, we weren't able to use real blood in our experiment. So we had to come up with a way to get a solution that had the same viscosity of blood. So I'm not gonna bore you with the painful math because I only have 10 minutes. But all the way on the bottom, you can see the mass fraction ratio of the water and glycerin solution that we created in order to have a solution that still is the viscosity of blood that we're looking for, but isn't actually blood. So in the material side of it, we are gracious enough to have been gifted a Quest MPS 3 system and the disposable set from Quest Medical. We use vegetable glycerin and water to create our blood analog mimic. And then we used the Medtronic DLP 10, 12, and 14 French cannulas as our handheld cannulas. We had pressure drones, transducer, Foley catheter, and we used the Sorin S5 in order to track our pressures. So this is how we constructed all those bits and bobs of random things into a circuit. So the top image might be the easiest to see exactly what's going on, but basically we connected the cardioplegia delivery line to a 3-way stopcock. This stopcock on one end is connected to our P1 pressure, which we use to measure cannula inlet. And then the other side is connected to our Medtronic DLP cannula of choice. The other end of the cannula is then inserted into a cut piece of an 18 French Foley catheter. This then sits on top of our mucus specimen trap. And the other open end of the mucus specimen trap is connected to the second stopcock, which will then measure our P2 pressure or our post-cannula pressure. So all of this really funky stuff for our P2 pressure was performed because we wanted to maintain a closed system so that all of our pressures stayed within the system and stayed accurate and unaffected by anything else in the environment. So we have a video for our methods here. For the sake of time, I will have to skip it. But it's lovely if anybody else wants to see it, and I can send it to them. So let's skip to the findings. This is the pressure flow graph that we created using the Medtronic DLP 10 French cannula size at different heights. So we chose no height difference, which is the exact same height of the delivery system outlet. Then we have a 12-inch height difference, which is 12 inches higher than that, and a 24-inch height difference, which is 24 inches higher than the original. And so, as you can see by this lovely graph, there appears to be a difference. So that graph was created off of this results chart here. Each, I guess, grid, each box represents 30 trials. So at every height and every flow rate combination, we ran the trial 30 times and used the averages in order to construct the graph that you see. And then afterwards, we ran a two-way ANOVA on the data controlling for height and flow rate in order to see if there was a significant difference. And as denoted by the very low p-values, there are statistically significant differences between the heights. And to make life easier, you will see that for the 12 French cannula, it was also statistically significant for the same controls, and also to 14 French cannula. So all in all, those are pretty cool, but how do the cannulas differ from each other? So then we created this pressure flow graph, and what is different between this one and the last ones is it captures the pressure drop of the entire system and not just the cannulas on their own. So we went all the way from the Quest MPS back pressure to the outlet of the cannula P2. So these pressures came from this results table, and I ran the ANOVA on this as well to see if they differed significantly, and they do. And if you were like me and thought, wow, that 12 and 14 French look almost overlapping, are those two different? I ran the second ANOVA on that, and they are. So all fine and dandy. And then we created these graphs, which is very similar to just the cannula graphs, but it's the whole system at different heights. So this is the 10 French, the 12 French, and the 14 French. So what did we learn? So we learned that both height and cannula size have a significant effect on the pressure drop when we're running our blood analog solution. And so this is true if you're measuring just the cannula itself. For our purposes, it was P1 to P2, but it was also true when you measured the whole system, which was back pressure to P2. And so we found that the higher the height and the smaller the cannula, the greater the drop you would experience. So why is any of this useful? So we need to be mindful that the back pressure reading on any cardioplasia delivery system is not going to be a one-to-one to exactly our clinical scenarios, and it might be useful to also have a direct pressure monitoring. Also, manufacturer assumptions about specific pieces of equipment don't always line up with clinical reality, because what they're testing for and what we experience don't always perfectly line up, and that's because they're simply not measuring for the same things. So, for example, the 10, 12, and 14 French cannulas, if you go in the manufacturer catalog, all have one pressure drop graph because their inner lumens are the same and only the tips are different. But because we're measuring, Quest MPS to pressure drop of the outlet of the cannula and not just the cannula in isolation, we find that there is an impact of the technique, and also the technique will play a role in how this differs even in other clinical scenarios in real life. So the last thing that this knowledge is useful for is it's important to test our individual equipment, and it doesn't have to be expensive, and it doesn't have to be unsanitary if you can also not use, for whatever reasons, blood as well. So this study is not perfect by any means. So our strengths, as mentioned earlier, is we are reproducible. We used inexpensive equipment. We didn't use real blood tissues. We didn't use real blood. So all of our equipment, it doesn't have to go through rounds of testing. It doesn't have to go through rounds of approval. And it's also an entirely closed system, so all of the pressure is maintained in itself. However, blood analogs are not blood. So it doesn't capture all the qualities of blood and different changes that are made in every single clinical situation. Additionally, when we used our 18 French Foley catheter as our coronary artery, it doesn't mimic the real properties of actual coronary arteries. So it's impossible to say with 100% certainty that this is exactly what you're experiencing at your clinical sites and at your different hospital systems. And the last one is this study was conducted at room temperature. Typically, cardioplegia is given extremely cold. However, for our purposes, we kept it at room temperature, though we know that blood viscosity will increase at colder temperatures, and as a result, arterioles will try and offset this increase in viscosity in vivo. So this is not, again, a one-to-one. But I would like to thank, first of all, my professors for guiding us through this process, though they couldn't be here today. And a special super shout out to Justine for helping us out, answering all of our questions, and being bothered by us by all of our emails this whole process. So thank you so much. And I'll take any questions.
If you don't mind, I have to say this is a very proud moment for me. I was fortunate to play a very small role in Taylor's development as one of her clinical instructors, and so my entire comment / question is that I'm very proud of you, and you look like you had fun up there today.
Thank you.
Taylor, thank you very much for a nice presentation. I have a question for you about your methods.
Yes. Let me go back.
There was a slide. Yeah, okay, you're going to find it.
It's in here somewhere. This one or this one?
Nope, last one.
This one.
Perfect.
Yeah.
So it looks like the flow is coming out of the MPS. It goes down to your handheld cannula, into the Foley catheter, into a sputum trap. And,
Yes.
And is that the end? End of story? Or is there some place it overflows into?
So it ends up, so what's actually being measured by P2 is the air displacement of, so essentially, right, we have the Quest MPS, the fluid will flow down that whole train, end up in our septum trap, and then it will, as it fills, displace air, and the air displacement is what's being measured by P2. The reason we had to do it that way, as opposed to like a direct measurement, is simply to keep the system closed. Otherwise, we'd have to open it, and then that would open up a whole spat of things that we can't directly control or measure for.
So how long did you run that before taking any given measurement?
So we ended up running it to 20 to 30 milliliters in the specimen trap because that's when the pressure is stabilized out. So before then, they were kind of figuring they were a little bit more all over the place. And then by the time we hit 20 to 30, we ended up having like a stabilization, and that's the pressures that we recorded.
And had you run that another 20 or 30 or a second or a third or a fourth 20 or 30, would the pressure have just continued to rise?
I can answer it. I did all of the running of the things. We would just empty it out. We wouldn't be continuously running the cardioplegia. We would run it, get our numbers, shut it off, empty the cup, and we did that lots and lots of times.
Really nice talk. Couple of questions.
Yeah.
How did you minimize bias in this experiment? Like, was it randomized? The way you were kind of altering your heights and all this. Like, did you do it sequentially every time, or was it randomized?
So it was done over the course of a couple days, and I guess me personally, I didn't run every single grid, right? Every single piece, because our group was 4. And so everybody had their section of height and flow combinations that they ran. And at the end, we pooled all of our results. So I wouldn't say it was randomized in the sense that I specifically ran every single combination once and somebody else then ran every single combination again. But
The question was more related to the sequence of the combinations. Was that randomized?
no, the sequence was we did 30 and then once we had all of them, we did the next one.
The other question I had was, what are the broad implications. Where to from here? Where do you see this project going?
So I think the next place that this project needs to go, and this might be just a general place maybe the literature needs to go, is I talked a bit about this Goldilocks zone for cardioplegia delivery, right? We want to hit a pressure that's not too high, not too low, but there really isn't a fair like ballpark number to go for. And this exists for a lot of reasons. Everybody's coronary anatomy is different. What do you do if there's blockages, you know? But as of right now, there really aren't any like, at least for the purposes of our literature review, any easily accessible ballpark numbers to go for. And I think before we can really say, before we can really continue specifically with what do these results mean in the broader literature, we need to figure out our Goldilocks zone first and then apply the pressure drops from there, if that makes any sense.
Thank you very much.
Yeah.